Welcome. From now onwards we will start analyzing the equations, first order partial differential equations for their solutions. Today's lecture is devoted to geometry of quasi-linear equation. So, in this first we set up the basic hypothesis and notations which will be assumed throughout the analysis of the quasi-linear equations, and then we discuss geometry of quasi-linear equations, the geometrical objects which are associated to quasi-linear equations. So, now prerequisites is that from now onwards to follow this course, definitely for the first order PDEs, what is very much required is an exposure to ordinary differential equation theory, mainly existence, uniqueness theorems for initial value problems, namely Picard's existence and uniqueness theorem, that is good enough. On the other hand, one more we require, that is dependence of the solutions on the initial data. That theorem will also be required, but not for this lecture, but in future lectures. Please refer to some good books on ordinary differential equations where you can find this material. Then from multivariable calculus, the most important theorem I would say is chain rule, and one should be very much expert with it. And change of variables, it looks quite easy while computing certain integrals which you would have done in +2, but actually it is not that easy, in the sense you have to be very careful. If you are not careful, it can lead to a lot of confusion. And then how a partial differential equation changes under a change of variables to a new equation, how to derive that, that is also very important. So, quasi-linear equations, hypothesis and notations. Omega 3 is an open and connected subset of R3. As I told you, omega d will be an open subset in Rd, but for the discussion of quasi-linear equations we have to take d equal to 3, because we are going to consider quasi-linear equations in two independent variables. So, omega 3 is an open and connected subset of R3. Why do we need connected? It is because we are going to take some curves in omega 3. Curve is a quite connected quantity, right. I mean, there is no gaps in that. Therefore, that curve should be in omega 3, otherwise also does not matter. That is why it is not that important at all here. It is enough, it is an open set. There is nothing wrong in assuming it is also connected, there is no loss of generality. Then the projection of omega 3 to the xy plane is denoted by omega 2, that is consistent. Omega 2 is a subset of R2. So, how do we define that? Those ordered pairs xy in R2 such that xyz belongs to omega 3 for some z in R. So, the functions a, b, c, which will be playing a role in defining quasi-linear first order PDE, they are assumed to be C1 functions on omega 3, that is continuously differentiable functions on omega 3, which is equivalent to assuming that all partial derivatives of a, b, c with respect to the 3 variables exist and continuous on omega 3. And we need this non-degeneracy assumption, which says that at any point xyz in omega 3, at least one of the two functions a and b should be non-zero. A way to express that is a square plus b square is not equal to 0 at every point xyz. Another way to write the same thing would be this: a of xyz comma b of xyz is not equal to 0 0. This is another way of writing the same thing. Okay. Why do we need this assumption? Is because imagine both a, b are 0, then this equation which we are going to consider, the quasi-linear equation, there is no differential equation, because at that point maybe a is 0, b is 0. So, it is just cxy equal to 0, some kind of degeneracy. So, we do not want that. That is the reason why we assume a and b simultaneously cannot be 0 at any point in omega 3. So, the quasi-linear PDE, we often use this notation QL Regularly we use QL. By QL we mean this: AUX plus BUY equal to C, A, B, C are C1 functions in omega 3 and A square plus B square is not equal to 0 at every point in omega 3. So, by just QL it stands for all these properties. Now, let us discuss the geometry of quasilinear equations. That means, this equation says something something about the geometry of what? Of a solution surface. If you have a solution of this equation, let us say u of x y defined for x y in some domain D, then z equal to u x y will be a surface, and this equation says what kind of restrictions are imposed on the surface. Geometrically what this PDE means for a solution surface, that is what we are going to discuss. So, integral surface, the definition of an integral surface, let D be an open subset of omega 2. What is omega 2? It is a projection of omega 3 to xy plane, and let U be a solution of the equation QL. Okay. U is defined on this domain D is a solution of the equation. What does it mean? The equation A of x comma y comma u of x y, ux of x y plus bxy, bxy uxy, uy of xy equal to c of x y u of x y is satisfied at every x y in D, that is the meaning of solution. So, the integral surface associated to U is defined as set of all triples x y z in x y belongs to D, right, and z belongs to R. So, x y z such that belonging to D cross R. So, it is a subset of R3 such that the third coordinate z is u of x y. It is also denoted often in short notation as S colon z equal to u of x y. In practice we say S colon z equal to u of x y is an integral surface. Caution, very important caution, remember that the function always comes with its domain, function always comes with domain. If you say that S z equal to u x y is an integral surface, it means that you have a function u defined on some domain, all this needs to be mentioned, or you know it, therefore you are not mentioning. But if you change the domain to some other domain, it can be still a solution, but it will be a different integral surface. We will come to these aspects in future lectures. Okay. The integral surface associated to a solution of the quasi-linear equation is actually the graph of the function. We are saying set of all x y z such that z equal to u x y just means the third coordinate is a function of first two coordinates, which means it is a graph of a function u, and any point on the integral surface looks like x y u x y for some x y in D. Therefore, this map is 1 1, x y going to x y u x y is 1 1, graph is always 1 1. Okay. The moment x y is different from x dash y dash, because the first two coordinates x y and x dash y dash are different, the triples x y u x y will be different from x dash y dash u of x dash y dash. They are different if x y is different from x dash y dash, because this itself is different. That is why the function is 1 to 1. Now, projection of the integral surface to xy plane equals D. Now, a fact from differential geometry, let S be an integral surface where u is a differentiable function. Okay, u is a solution, right, therefore, it must be a differentiable function. Actually, in this fact we need not have integral surface written, it is true for any surface, that is why I wrote let this be a surface and u is a differentiable function. And why we write integral surface here is because we are going to discuss, we are worried about only integral surfaces in this lecture. In fact, in this PDEs we want to find solution, therefore, we are interested in surfaces described by solution of the equation. So, take a point P naught on the surface, okay. Then a normal to the surface S, normal to the surface at the point P naught has this direction ux uy minus 1, okay, ux uy minus 1. There is a more general result, I will write only roughly, okay. Phi of x y z equal to 0. If this is a surface, then what you have is grad phi, okay. What is that? Namely phi x, phi y, phi z, that will represent a normal. Of course, this should be non-zero. So, all that conditions will be there, and in our case what is phi? Phi of x y z is equal to let us write in this form u of x y minus z, and its gradient is nothing but ux, uy and minus 1. So, that is true at every point. Okay. So, this is a more general fact that this is normal. Therefore, quasi-linear equation is nothing but the dot product of this ux, uy minus 1 with ABC equal to 0. What you get is AUX plus BUY equal to C. That is the meaning of saying it satisfies the PDE at the point x0 y0. In other words, the ABC which defined our quasi-linear PDE is a direction in the tangent space to the surface S at the point P naught. Always you have to remember this phrasing, tangent space or tangent plane if you are in plane to something at some point. Okay. So, this is a tangent direction, we caught hold of a tangential direction in a what would be a search for a integral surface. We know that I do not know that surface in the sense that I do not know solution, but I know a vector which is in the tangent space at a point on such a possible surface. This idea will be useful in finding solution later on. So, by definition of tangent space, there is a curve on the surface with what property? So, imagine this is a surface, okay. This is a point P0, then through this you have a curve gamma passing through that point, and at this point the tangent vector is A of P0, B of P0, C of P0. That is the meaning of somebody being a direction in the tangent space. So, tangent to the curve at the point P0 is in the direction of AP0, BP0, CP0. Now, what do you mean by that? There is a curve with this property, this is the meaning. There is a delta positive and a curve gamma described by a function r from some small interval minus delta delta, what all you need is 0 should be there in the interval such that gamma lies on the surface, this curve is on the surface and it passes through the point P0 and the tangential direction is this. This is the tangential direction that coincides with ABC at that point P0. These geometrical considerations motivate definitions of characteristic direction, characteristic vector field and characteristic curve. For a clear understanding of these geometrical objects, you may consult books on differential geometry written by DeCarmo or another book by Millman and Parker, where these are very clearly explained. Now, we are going to define characteristic direction and vector field. The direction of the vector ABC is called the characteristic direction at the point xyz in omega 3. Now, the association to every point in omega 3, okay, take a point in omega 3, associate at that point an infinitesimal line element having this direction ABC. This association is called a characteristic vector field. Basically, vector field means you are associating you are associating a vector to each point. So, it would look like we can't write things in 3 dimensions, but let us see, this is, imagine this is your omega. I will not write what is, maybe you can write 3, any point you just put some lines like that. Okay. These are the directions of ABC at that point. So, of course, it varies from point to point and so on. So, this is called characteristic vector field associated to the quasi-linear equation QL. If you change the equation, ABC will change, therefore, this association will also change. Now, characteristic curve. A curve gamma lying in omega 3 is called a characteristic curve for the quasi-linear equation QL if at each point on the curve gamma the tangential direction to the curve is same as the characteristic direction. Both directions coincide. That is called a characteristic curve. Now, if you project the characteristic curve gamma which is in omega 3 to xy plane, that will be called base characteristic curve. It is called a base characteristic curve. So, base characteristic curve lies in omega 2, which is the projection of omega 3 to xy plane. Characteristic curve lies in omega 3. Now, we have a characteristic system of ODEs. The characteristic system of ODE for the equation QL is the system of ordinary differential equations dx by dt equal to A, dy by dt equal to B, dz by dt equal to C. So, it is an autonomous system of ordinary differential equations with the right hand side A, B, C coming from the equation QL. Now, let us look at an example. For this PDE ux equal to 0, very simple PDE, let us say it is PDE in 2 variables x and y. The characteristic system of ODE is dx by dt equal to A. In this example, A is 1, B is 0 and C is 0, therefore, dy by dt is 0, dz by dt equal to 0. We can integrate them, x of t equal to t plus constant, y of t equal to another constant, z of t equal to another constant, where C1, C2, C3 are real numbers. Now, what is it geometrically? What we have to look at is t plus C1, this 3 tuple t plus C1 comma C2 comma C3 as t varies in R, t belongs to R. This is what we have to look at. Of course, to write down this, fix C1, C2, C3, fix C1, C2, C3 and look at this. Okay. This is a line, right. Second coordinate, third coordinate are fixed, first coordinate will give you entire R. So, this is precisely what you get is R cross singleton C1 cross C2 cross C3. This is precisely that. Second coordinate is fixed, third coordinate is fixed, first coordinate can be any real number. So, that is what we get. So, characteristic curves are the family of straight lines which are given by the intersection of the plane y equal to C2 and z equal to C3, which are nothing but the translates by points of the yz plane of x axis. So, this is a picture specific to some particular quasi-linear equation. Ux equal to 0, equation is ux equal to 0 and uxy equal to sin y is a solution given, you can verify. It does not depend on y. Ux equal to 0 means it is constant, right, with respect to x. So, it is a function of y only. I have taken that to be sin y. Now, this is a graph, the sine is going like that, right, the curve you can see the sine curve like that. Okay. Now, in this red axis, red is always x axis, green is y axis, blue is z axis. So, this is x axis, green is y axis, blue is z axis. Now, characteristic curves are in black, which are straight lines, we know that straight lines, and characteristic vector field is in red color, which is this, okay, because characteristic vector field is 1 0 0 at every point. So, it is in the direction of E1 every point, and normal to the solution surface is in magenta. So, it keeps changing the normal from point to point. So, blue surface, this is just an observation and this is in fact also a general situation, we will show the theorem later on. Blue surface Okay. That is what integral surface corresponding to the solution u x y equal to sin y. So, z equal to sin y is this. Okay. That is union of these black lines. So, you can think one line, this line keeps on moving and you get the surface. Okay. A remark on characteristic curves. For the quasilinear equation, characteristic curve lies in omega 3 and base characteristics lies in omega 2. This is very important. Many times this word is blurred. So, people refer to both of them as characteristics. So, you have to be very careful. Therefore, to clear this problem or confusion, we use the word base characteristic curve. Now, if A, B, C are C1 functions, then a unique characteristic curve passes through every point of omega 3. What is a characteristic curve? It is the solution of x dx by dt equal to A, dy by dt equal to B, dz by dt equal to C, its image. This is guaranteed by Cauchy-Picard-Lipschitz existence and uniqueness theorem in ODEs. Therefore, two distinct characteristic curves do not intersect, by otherwise uniqueness will be violated if they intersect, unless one of them lies completely on the other, unless one is on the other. In other words, we may ask what do you mean by one lies on the other. So, it may be that you have a solution which is that long. If you look at a small piece of that is all the solution. So, this is the only way uniqueness is violated. Okay. So, therefore, we do not consider such things as different solutions. So, therefore, two distinct characteristic curves do not intersect unless one of them lies completely on the other. Base characteristic curves corresponding to two non-intersecting characteristic curves may intersect. This can happen. Characteristic curves do not, but their projections can intersect. Intersecting base characteristic curves prevent Cauchy problems from having global solutions. We will discuss them further, but this is a fundamental obstacle. Now, this is an exercise for you to think over. Base characteristics, they also arise as solutions to ODEs. If base characteristics intersect, does it contradict Cauchy-Lipschitz-Picard theorem? Does it contradict that theorem? Of course, things are working well, it should not contradict, but then this confusion is there, right, because they are also solutions to initial value problems of ODEs. Okay, we will clear that later. So, when the quasilinear equation reduces to a semilinear equation, what happens? A, B are not functions of the third variable anymore, they depend only on the x and y variables. Then neither distinct characteristic curves intersect, that we know even for quasilinear equations, nor the corresponding base characteristic curves intersect. Because what is a base characteristic curve? It is a projection of the characteristic curve to omega 2. But solutions of which equations? Because it is semilinear, the equations are dx by dt equal to axy, dy by dt equal to bxy, okay, and AB are C1 functions still. So, by Cauchy-Lipschitz-Picard theorem, there is exactly one base characteristic curve passing through every point of omega 2. That is why. Semilinear base characteristics do not intersect because the equations governing the base characteristic curves, the right hand side is A and B and they are functions of x y only. If they are also functions of x y z, you cannot claim uniqueness because you cannot solve, the problem is does not make sense. Okay. Now, a surface in R3, okay, how does it look? It looks like a plane but slightly deformed, right, that is a feeling. Therefore, it looks like there are 2 degrees of freedom to move on a surface. If you are a surface like this, you can move like this, right, 2 degrees of freedom. It is not like one single straight line, right, like a road on which you can't overtake. Okay. On the other hand, we also know the following: the family of characteristic curves are determined using solutions of initial value problem, which by design have 3 degrees of freedom, because it is a system of 3 equations being solutions to a system of 3 ODEs. Now some question, do you think both statements are correct? Answer is yes, they are both are correct. Are they contradictory? Because you are saying on one hand there are 3 degrees of freedom for these curves which are lying on the surface, surface itself is 2 degrees of freedom. Are they contradictory? Answer is no. Clarification to this is the following: solutions to the characteristic system of ODE, they form a 3 parameter family. Why? Because they are parameterized by the points of omega 3. So, take a point in omega 3 x 0 y 0 z 0, and then for any given x 0 y 0 z 0 in omega 3, there is a solution to the initial value problem which we call Cara ODE. This stands for dx by dt equal to a, dy by dt equal to b, and dz by dt equal to c with these initial conditions. At t equal to 0, x 0 y 0 z 0 is x 0 y 0 z 0. Now observe the difference between a function and its image. Image is often called trace or trajectory. It is just image. Okay. Trace is not a graph. On trace, no information of j is retained. We will look at an example. Look at this t belongs to r going to cos t sin t, it is a function. Trace is a circle, that means set of all cos t sin t as t varies, this is a circle which is in R2. Graph will be a subset of R3, graph will look like t comma cos t comma sin t, that is not a circle. So, this is the difference between solutions of the system Cara ODE and the characteristic curves which are images of this or trace or trajectories of the solutions described by solutions of the Cara ODE. For ease of presentation, let us assume that A is never 0 in omega 3. Okay. Once it is never 0, you know what I am planning to do, I am planning to divide. Now I will eliminate the parameter t from this Cara ODE system. Okay. T will go, then I will get dy by dx equal to b by a and dz by dy equal to c by dz by dx, I think. Let us see. We conclude that that is satisfy, yes, dy by dx and dz by dx. I eliminate t. It means that I am assuming something about it. Let us not discuss that right now. So, note that solutions of 1 forms a 2 parameter family, system of 2 equations. So, 2 parameter family. Justification is exactly same that we gave for system of characteristic ODE, system of 3 equations, 3 parameter family. Okay. Similar explanation gives you that it is a 2 parameter family. Now, you see here the t has vanished in this, right, there is no t in this. Okay, reparameterization of a characteristic curve. What is a reparameterization? Let gamma be a curve, that is gamma is the image of a function r from some interval j to omega 3, where j is an interval in r. This is a curve given. Now, we are going to define what do we mean by a reparameterization of this. It is a function phi defined on some interval j tilde to j, okay, j tilde to j, where j tilde is an interval, that is it. With what property? It is a diffeomorphism, that means the function is 1 to 1 and onto, so that is function is bijective, and therefore, the function and inverse makes sense, both of them are differentiable. Now, image of this function r circle phi, which is now defined on j tilde to R3, coincides with gamma. So, the image of r circle phi and r are the same, both are gamma. So, that is a reparameterization. Now, if a curve is described by 2 parameterizations, then is it true that one appears as a reparameterization of the other? In other words, you are given r from j to omega 3 and r tilde from j tilde to omega 3 such that images are same. Now, the question is there a function phi from j tilde to j which is a diffeomorphism? Answer is almost true, but you have to assume some more properties about the parameterization being regular. So, this you can once again look up books of Do Carmo or Millman-Parker on differential geometry. But our question is not about this, we are not asking this question. Now we are interested in reparameterization of a characteristic curve. So a curve can be parameterized in infinite number of ways simply because the functions that we have here phi tilde, the function phi from j tilde to j, you can take any interval j tilde, okay, and you can always define any interval means the open interval j tilde, then you can always find a diffeomorphism between j tilde and j. So therefore parameterizations are infinitely many. So curve is a geometric object, the image is a curve, that is a geometric object, while parameterization is a function whose trace is the curve. So at any point on the curve, the tangential direction does not change with parameterization, should not change, because tangent is a geometric object associated with a curve. So characteristic curves fit the characteristic vector field. That means you have a characteristic vector field, characteristic curves are precisely those curves at each of whose points the tangent is the characteristic direction. Okay, this is not coming under reparameterization, but we wrote this because we will see this, we will use this. Yeah. So the following lemma is a restatement of the geometric fact discussed on the previous slide in the context of characteristic curves. Any reparameterization of a characteristic curve is also a characteristic curve. Remember, it is not about a curve, it is a characteristic curve. It means the tangent should be the characteristic direction. In this context is this statement made here, the last one. Okay. You know that the characteristic vector field is the same, right, and tangents are geometric objects, characteristic curves are somebody who fits this. Therefore, the next theorem is expected, this lemma. And therefore, one advantage of this is you take j tilde to be R, okay, R to that particular j, you can always define a diffeomorphism. Therefore, you can always reparameterize by R. It is very useful, we will see that when we prove existence theorems for the Cauchy problem of quasi-linear equations and as well as general nonlinear equations. So, proof of the lemma, let gamma be a characteristic curve. That means first of all it is the image of a function. Let us write, because it is sitting in omega 3, there are 3 components, let us write RT equal to xt, yt, zt, and xt, yt, zt are solutions to the characteristic system of ODE. Let phi be a reparameterization of gamma given to us, phi is given, j tilde is given such that this phi is a diffeomorphism. This is the meaning of diffeomorphism. Now R tilde is R circle phi, and R tilde let us use a different running parameter in j tilde. For j we use t, for j tilde let us use tau. R tilde of tau is x tilde tau, y tilde tau, z tilde tau. We want to show this is also a characteristic curve. It means we have to find the tangent to this curve and show that it is a characteristic, has the characteristic direction. So x tilde tau by definition is this, R tilde is R circle phi. So x tilde tau equal to x of phi of tau, y tilde tau equal to y of phi of tau, z tilde tau equal to z of phi of tau. So differentiating each of the equations in 2 with respect to tau gives us the following equations in 3, which is actually chain rule. Now xt, yt, zt solve Cara ODE, therefore we know that dx by dt, dy by dt, dz by dt are a, b, c respectively at the point x of phi of tau, y of phi of tau, z of phi of tau. So this is the equation we get. Now in view of the relations 2, what are those? Relation 2, it is the definition x tilde, y tilde, z tilde gives us these equations. Okay. Since phi is a diffeomorphism, we have d phi by d tau is non-zero at every point. So that means this quantity which is multiplying ABC is a non-zero quantity. Therefore, the direction of this right hand side is same as the direction of this ABC, because it is non-zero. If it is 0, we can't say this is non-zero because of the diffeomorphism. So, proof of the lemma is complete on observing that there is a diffeomorphism between any open interval and R. Therefore, we can reparameterize a characteristic curve by R. Importance of this lemma is it gives us a consistent usage of the terminology. A characteristic curve for QL should be an intrinsic property of the PDE. It should not depend on the parameterization used. Remember the definition you was using parameterization. This is confirmed by this lemma. And parameter T is artificial. Okay. So, maximal interval of existence for any solutions need not be R, even for autonomous systems. For example, look at dy by dt equal to y square and y of 0 equal to any number you take y0. Solution will not be defined on R, even though the ODE makes sense for all t in R. Therefore, there is a concept of maximal interval of existence, it will not be R. Okay. Even if it is an autonomous system, as we just saw in this example. But thanks to this lemma, we may assume that solutions are defined on whole of R. Equation is different, our interest is only in the trace, right, in the trace of the solution, in the image of the solution, that is same. So, it is not surprising that the lemma holds, since the parameter T itself was introduced by us. Equation gave us ABC, we said yes, there is a curve whose tangent is this, therefore, we said curve means R of t, x of t, y of t, z of t, its derivative equal to ABC. We did that, we introduced the t. Therefore, it is already artificial, it is confirmed. In fact, this usage is there in Fritz John's book. He also says this parameter is artificial, which is this lemma confirms. Now, characteristic curves fit the characteristic vector field. For autonomous system of ODEs, the RHS may be thought of as a tangent vector field, right. Solving this system means to find curves which fit the vector field. Thus, as long as we are interested in the trajectories of solutions, we may assume that trajectories are parameterized by R. This observation reconfirms that the parameter T describing a characteristic curve is artificial. The above interpretation, that is parameter T is artificial, does not hold for trajectories of the non-autonomous systems of ODE. The proof of the lemma suggests where the proof will fail, and hence that is the reason why this will not hold. Let us summarize what we did now today. We introduced the notions that will be used throughout the discussion on quasi-linear equation notations. We have introduced the notations, and then we discussed the geometry of quasi-linear equations, which led to the introduction of concepts of characteristic vector field and characteristic curves. We analyzed the degrees of freedom for solutions of a Cara-ODE and characteristic curves. We proved that a characteristic curve may be parameterized by R. So, using this geometry of quasi-linear equations, we try to solve Cauchy problem for quasi-linear equations in future lectures. Thank you.